time this is all done. So, today is very much a proving a limit is a limit. And this is usually taught the first 2 weeks in a college calculus text. And then usually there's a big beeline of people going to the registrar to drop the class right after that lesson. Because it's just too much early. You're learning this late, and so you can handle it. And because you're so darn smart. It goes a little something like this. Let's introduce the idea of this one. As x goes to 0, what does x over x approach? 1. I don't like how you said that. I don't want you to say 1.
One.
What you say?
One.
One. It's 1. And that's because, although 0 is a problem, a limit's not at 0. It's the approach, and as you get closer and closer, they always knock each other out, and it's 1. Look at this graph. What is the limit as x goes to 2? 2. Why isn't it 1? Isn't at 2 the y value 1?
No, it's non-continuous.
Okay, it's not continuous, so, I mean, isn't the limit just whatever the function is? No, it's what the function approaches, and so it's 2. All right, so would you tell me, what is the limit as x goes to 2 of 1 half x plus 2? Okay, now wait a second. There's no way you did an approach that fast. You said 3. And did you actually say, all right, what happens when x is 1? And what happens is when x is 1 and a half? And what happens when x is 1 and a 9? Or 1.9? You did? You did not. You found that much quicker. How? You plugged it in. You said direct substitution. Yeah, I have a problem. Okay? You just said the limit is the approach, not the f. And you went at. Why can you use that? Because it's continuous? Okay, how do you know it's continuous? Because by definition, you know it's continuous because the limit approaches. So if I understand you right, you're saying the limit is 3 because it's continuous, and it's continuous because the limit is 3. Is that what you're saying?
Yeah, pretty much.
That's the worst reasoning. Okay? That's called circular reasoning, and it's trash. It's garbage. Okay? You say it is because it is, and that's nonsense. That's not true, and it's terrible math to begin with. So instead, let's actually try this in a little more rigorous way. I don't find that. You just told me the limit is the approach, not the at, and so you must approach. So here we go. If x is 1, what is the function when x is 1? 2.5. Okay. All right. What about when the function or when the x is 3? 1.5 plus 2 is 3.5. Now you might say, hey, see, there's 2. It's between 2.5 and 3.5, so the limit is 3. To which I respond, yeah, why not 3.25? It's between the two. Why not 3.25? Because it's linear. So, oh, you're saying the linear has to be halfway theorem. Is that what you're saying?
That's not a theorem.
That's not a theorem here. Let me get you a textbook, and you can find that theorem in a textbook. And if you find it, I will give you my year's salary. Okay? All right. Yes. So it's not actually a theorem there. So, all right, I don't buy it. 3.2, there's way too big a cap in here. There's still a million things that could be too big. No, don't buy it. So you say, okay, I'll get a little closer. If I get a little closer to 2, say 1.9, what is, this scares me to even ask it, but what's half of 1.9 without a calculator? 0.95 is what I was hoping for. And half of 1.9 is 0.95, plus 2 is 2.95. At 2.1, what's half of 2.1? 1.05 plus 2, 3.05. To that you say, okay, see, there's no way 3.25 can be, that's not in there anymore. That's not it, you're nonsense, that's crazy talk. It's got to be 3. To which I respond, why not 3.03? That's in there. Maybe it's 3.03. So you get a little closer. 1.99 divided by 2. 1.99 or 0.995 plus 2 is 2.995. 2.01 divided by 2 is 1.005 plus 2 is 3.005. Then you can say, see, 3.03 is not in there anymore. It's way outside of that range. And you say there, boom, now it's got to be 3. And you can imagine then I could keep coming back over and over with, oh, still don't buy it, nope, still don't buy it. Now, at that point then, you could say, you know what? You tell me, how close do you want me to get? Because I can get you there. If you'll believe it, if I could get 2.9999995 and 3.00005, will you believe it then that it's 3? If you can do that, then I'll believe you. That's the idea of a delta epsilon proof. If there is some kind of epsilon away from the limit of 3, epsilon is some difference between the f values and the limit. Now that epsilon looks like a backwards 3, I suppose. It's lowercase Greek letter. Now, to get that epsilon, once I said, all right, you get me within a trillion, I'll believe you. You would then have to figure out, all right, what do I put in my calculator to get there? Now that, how close you would have to get x to 2, that would involve you saying, all right, how close do I have to get an x to 2? That's delta. Now that's not capital delta like you're used to. That's lowercase delta. And think of it like an 8 where you got lazy and got tired. Okay, you just stop. It's like a partial 8. That delta is how close you need to choose x's to what you're approaching, the approach value. All right. In a visual sense here, think about it in these terms. Now, surely again, let's remember the idea of the day is the limit is the approach, not the x. So don't give me that, hey, see, when you put in 2, the limit is 3. That doesn't mean anything to you. That's not what a limit is. A limit, I can get as close as you want here, and it's still not going to convince me that it's not 1. So the idea is there's got to be some degree of closeness where if you could get the table outcomes less than this way away from 3, then I'll believe you. That, again, what's this gap between how close you need to get the function to the limit? Is that delta epsilon? That's epsilon. Okay, this is the epsilon you want to get close enough to. Now you actually start, when you make a table, you don't start with the y value, you start with the x value, right? So you really go about tracing back that and saying, all right, I need to get a delta so that if the gap between x and 2 is less than that delta, if that gap is small enough, then it'll follow that the gap that they want will be small enough as well. So anything less than that would certainly suffice to make it less than the gap you want. All right, the visual helps some people but confuses others. And so if you're visual, then take it for what it is. All right. I kind of already said all this stuff here. If you have this in your notes, then that's pretty much what I'm saying here. Delta is how close you need to get the x's to the value you're taking the limit at. And epsilon is the how close you got to get the function to the limit for them to actually believe the limit is what you say it is. Let's look at the definition of the limit. This is the formal definition of the limit. Now, the greatest calculus people were by far Leibniz and Newton. But after that, they had tons of holes in their calculus. It was not something you could, what most mathematicians would call you could rigorously prove in a lot of ways. So after them, one generation later came what I think of as the janitor of the calculus, and that's Cauchy. he is the one that came up with a lot of the formal definitions of the calculus that you do, including the idea of a limit here. This is the actual definition of a limit. The layman's definition of a limit is what does the function approach as x approaches a certain value, and that surely makes a lot of sense to someone just learning the calculus. But the true definition of the limit is if you're given a function, the limit is L only if it can be demonstrated that there is some delta that you can find so that when x is within a delta, you can read that as if x is within delta of what you're approaching, that it must follow y is within some arbitrary delta epsilon of the limit. Now the proof of this involves saying, yeah, I can get you there. Epsilon, whatever epsilon you want, a trillionth, a billionth, just let delta equal this, and watch. When x minus c is less than that delta, it'll have to follow that y minus the limit is less. The limit then, or the proof of this, will look something like this. When you write a proof, the very first thing you need to do is say, all right, here's my delta. Let delta be this. I'm going to prove that when this delta is used for this problem, the problem all holds together and it follows. Now, the delta, for linear functions, delta relates to epsilon through the slope. Come over here, I drew it to scale. I had a hard time drawing on the whiteboard because when I put a ruler up to it, it kept jumping around. So, I didn't, I think I fudged the y-intercept, was it? Oh, maybe I didn't. Okay. So, here's, I did fudge the y-intercept. That's okay. This has a slope of up 1 over 2, okay? The y-intercept is just off. I was just pointing out here. So look at this. When the delta was 1 box, inch on either side, when you trace that back through the slope that was up 1 over 2, the delta is actually twice as big. You see, a little gap results in a bigger gap in x. Do you follow me? So it's 2 inches there. So if I were to say what's the relationship of delta to epsilon, it is epsilon over the slope. Write that down in your notes and we'll change. Thank you, Lily. So delta is epsilon over the slope of the problem. There's kind of an inverse relationship. The bigger the slope, the smaller the delta, and vice versa. Okay. Now then, we're going to then, for this problem that we were just doing, we're going to say let there be a delta that satisfies the proof, and the delta is epsilon over a half, or 2 times however close you want me to get. If I let delta go, or the gap around x be twice as big as however close you want me to get, it must follow that the limit, I can get as close as you want to the limit, all right? Now, when you go to prove this if-then statement, you assume the if and you prove the then. So we're going to assume, or we're going to show, actually let's just go with the thesis. But I'm going to show that if x minus, and I said x minus c generally in the definition, but in this case it's if x minus 2, or the x's numbers around 2, okay? So if the difference between whatever x I choose and 2 is less than delta, then it follows that the y values and their difference from the limit, which in this problem is 3, will be less than that however close you want me to get, and that's epsilon. Now, we assume, as we said, we assume the if. I'm going to say, all right, let's say I go with the assumption that it is true that x is within delta from 2. Is another way to say x minus 2 is less than delta is x is within delta of 2, yeah? Well, by definition, isn't delta 2 epsilon? All right, so surely if x minus 2 is less than delta, then x minus 2 is less than 2 epsilon. Now I'm trying to get here. And we practiced this a little in a couple of homeworks lately, but just so we're clear, to get from here to here, we're going to have to do some playing around with this inside stuff. F of x, to get here, wouldn't I need to get to something like this? I need to get here. Now that's what goes through my mind. I don't, and we'll put it in your notes, but eventually you wouldn't say, hey, this is, you wouldn't say, okay? How do I get from where I'm at to there? What accepted math could I do? Divide by 2. I can divide by 2. Do I have to switch the inequality if I divide by 2?
No.
When do I have to switch the inequality?
Negative.
When it's negative. All right. So I'm safe there. All right. Cool. This guy over here, would it be the same if I took the absolute value of x minus 2 and multiplied by a half as if I multiplied by a half then took the absolute value? Would it be the same outcome either way? Okay, so I could multiply this in. All right, cool. Now I see the half I'm trying to get. That's cool. How do I get that? Oh yeah, what's 1 equal to? It has to be the case that f of x plus 2 minus 3 is less than epsilon, and therefore, if x minus 2 is less than delta, it has to follow that f of x has to be within epsilon of 3. And that dot, dot, dot is the therefore of the proof. It's the end. If you really want to get fancy, know this on there. That's fancy pants math at the end of a problem. I don't know Latin words. Somebody know? Quoad demonstrate. It means basically that's what I was trying to prove or demonstrate. Okay, I don't speak Latin, but QE Dewey is quoad demonstratum, I believe. Anywho, that's the proof. It's very much a proof, so it's a process. They're following you. You don't want to lose people. You need to go slow. So let's try one with a negative slope. This requires you to do a little different work, and we'll have to think about that. But let's start here. What's our delta? Let delta equal epsilon over negative 3 halves. Now I can tell you that's going to be a problem because first of all, it'll switch the inequality. Second of all, it's going to cause heck with everything. So go back to your notes and in fact switch it to this. Let delta equal the epsilon divided by the absolute value of this is what it shall be. Okay? So we're going to say let delta equal the epsilon over the absolute value of negative 3 halves, which makes it 2 epsilon over 3. You follow? All right. I will show that if x is within delta of what this time? 4. If the difference between x and 4 is less than delta, or x is within delta of 4, then it must follow that the difference between the function and the limit, which is 1 in this case, is less than epsilon, and epsilon is just any degree of closeness you want me to get in the table, all right? So how do I get going with my proof? This is what I'm trying to prove. So you assume x minus 4 is less than delta. And then what? All right, by definition of our delta for this problem, x minus 4 must be less than 2 epsilon over 3. Then what? So if I multiply by 3 halves, do I need to switch the inequality? That's awesome. That's why we use that absolute value. All right, now here's where we need to do a little bit of creativity or creative work with the negative. We want it to end up negative, right? When we get f of x in there, you follow? Tell me, is this true? Is 3 halves the same as the absolute value of negative 3 halves? We can all agree that's true? Alright. Now, most people say that's true. This one, you have to think about. But what about multiplying absolute value? If you take absolute value of each factor, then multiply, would you get the same thing as if you multiplied, then took the absolute value? You do. That is an accepted truth. Okay? And so it is the case that the product of these two absolute values is the same as the single product, negative 3 halves x plus, what do we get there? 6. Okay? Cool. Doing great. What now? 1 f of x minus 1. I got part of the f of x. I got the negative 3 halves x. But how do I get the 7? Break it into negative. Oh, sorry, not negative. 7 minus 1. We all agree that 6 is 7 minus 1? And by definition of x, f, rather, they gave me, that is f of x minus 1. Must be less than epsilon. It must follow that y is however close you want as a consequence. All right. Would you try one on your own? Right. How's it going? Did you let delta equal epsilon over 2? Did you eventually get to the point where you had to do 2 replaced by an absolute value of negative 2? And then inside, did you have to break up 2 into 7 minus 5? Therefore, getting you f of x minus 5. All right. Good? Okay. Everything doesn't seem that hard to me. You're right. It's not that hard. Linear is not that hard at all. But assume tomorrow that instead of in a line where the gap stays the same on either side, you curve. If the gap is 1 inch on either side, when you trace that back through a curve, now the gap is different on each side, and it's decision time. Which delta do you use? That is tomorrow. The textbook only gives you linear delta epsilon. That's ridiculous. If this is supposed to be a college level course, then you need to be able to do curvilinear as well. And so tomorrow we'll do curves. All right. Good deal. Questions on set 101? 3. 1. 3, 1, 2,
25.
25. 3, 1, 2, 25.
I was trying to use linear. It wasn't working.
drumsticks are doing one of these, and these aren't easy when you're in this mode, so here we go. So they tell you about these drumstick sales, and they want to maximize hourly income. So reminding you of the maximization process, much harder than the related rates, I think. You ask yourself, what are you trying to do? You're trying to maximize revenue. Clearly understand the question. It could be maximizing or minimizing, it could be doing cost or area, it could be a lot of different things. So you've got to be clear on what you're trying to do. Then you need an equation for that. Now when you're selling drumsticks or anything, how much you take in, not profits, revenue. How much you take in depends on two things. What? When I'm selling a bunch of stuff out of the trunk of my car, how much money I collect at the end of the day depends on how much each one costs and how many I sell, right? What variables do you want to call those? N for number of sold and P for price, unit price. Sounds good. Okay. Now, we get into the calculus and we want to maximize, that's our prime positive to negative, but we know, having done lots of calculus, that if we can avoid doing calculus on three variables, we should. What kind of other relationship to get down from three variables to two? Well, that's where the meat of the problem is. That's where it starts to get difficult. So it says the base case is when the number sold is 30 drumsticks, the price is $2.50 or vice versa. I'm going to make that 250 if you don't mind. Cents. You cool? All right. They say that for every 25 cents she decreases the price, she can sell 5 more drumsticks per hour. All right. So for every 25-cent decrease results in 5 more sales. All right. Now all that's great, and I know there's a relationship in there somewhere. What is it? Is this what kind of relationship is implied by for every? If the change always ends up being the same kind of thing, then it's linear. So it's linear. All right. So I don't know about you, but if I were when I was doing this after taking a break from calculus for 5 years, I just kind of, it took me forever, but I kind of just muddled my way through. I know it's linear. And I said, all right, what's x, what's y? Which is the dependent variable and which is the independent variable? Price. Do I get to choose price or I get to choose price, right? So does that make price x or y? All right, so this is price, and the response variable or the dependent variable is the number sold, and it's the y, right? All right, I'm getting somewhere. Now, what about that change kind of thing? M is normally change in y over change in x. So what's the change in y? The 5 more sales or the 25-cent decrease? 5 more sales, and that's 5 more, so that's a plus 5. The change in x is change in price, and that's a 25-cent decrease, so that's negative 25 or negative 1/5, and we can put units on that if you want, but I'm not going to. Okay, so the equation might look something like n minus 30 is negative 1/5 price minus 250 cents, or n is capital up. So n is 30 minus 1/5 p plus 50, or 80 minus a fifth p. Can we agree on that? All right. Now we're ready to roll here. That's the hard part. Now we're on 3. So the easiest revenue function, as dependent on price only, is 80p minus 1/5 p squared, and now you're rolling. R prime positive to negative. The derivative is nice and easy. You should be on your way. All right. I'll give you a second to finish that up, and then we'll talk about number 1. Number one, man, this one's very much a structure kind of deal. You have to be organized to do this well. One, I would imagine 1A was probably okay. They say, they say the radius, I'm going to use big R here, because later on in part C, they give you the little circle, which is I'm going to call little r. So they say that dr dt, the circle is growing with the radius growing by 5 centimeters a minute. I remind you, be intentional about the sign, yeah? Now obviously if the radius is growing, then the area is growing over time. So do we need to talk about A, or are we good on A? All right, let's go to Giger and see where it starts to get crazy. They say, given that R is changing, how fast is the area of the square changing? So they want the ADT at the instant when R is 10. Okay, cool. Can't find the ADT if I don't have an A equation. That's A of the square, that is. Okay, so give me an area of the square equation. 4x squared or just, oh, you might be way ahead of me. Do you agree that the area is definitely x squared, if I let this equal x? And let's, so you're relating that to R, yeah? Is this a 90-degree angle? Okay, cool. So x squared is 2r squared. So I see where you're coming from. So I guess I was about to solve that for x, but can't I just say, well, that's what I want. X squared is 2r squared. So in place of x squared, could I say that's just 2r squared? Very cool. There you go. I thought I remembered a root 2 being in there, but I guess not. Okay, we're cool? All right, so dA dt. What is dA dt? Or our dr dt. So at the instant they talk about dA dt, somebody use a hairspray in here? You smell that? Is that hairspray or blueberry? I can't tell which.
Smells pretty good.
Oh, yeah, it's not bad. Somebody was allergic, I don't know. 4R is, who does that during calculus class? I need to put some hairspray on. What the heck? Whatever. All right, so I'm getting 200 here. Are we done? 200 centimeters squared per centimeter minute. Per minute, yeah. Good. Are we good on part B?
Yes.
Then C is even a little more crazy. So C says, all right, now a circle is inscribed in that square. And now we need to talk about a new relationship. Surely the area, they want dA, I'll call it IC for inscribed circle, dt. What is the area of the inscribed circle? Well, I guess it's pi r squared, but really the big idea is, how does this little r, which I guess I'll draw here, how does little r relate to either x or big R? It is equal to x or equal to half x? I agree. R is equal to half x. R is equal to half x. And should we take that all the way to big capital R? We said that x is, let's see, what should I do? Should I square it first and then substitute, or should I, what should I do? Are you just waiting to copy it down for, jump in here, people. That's the most expedient way to do this. X is root 2 capital R, yeah?
Yes.
So that means little r is 1/2 root 2 capital R, or root 2 over 2 big R. So the area of the inscribed circle is pi root 2 over 2 big R squared, or 2/4 pi over 2 big R squared. That's kind of cool. It's half of the outer circle. That's kind of wicked. Okay, at any rate, that's surprising to me. I don't know why. Are you good from there? Okay. Cha. Okay, 2. Is 2 still a question? Yes. 2. Is 2 replaced? Yeah. Oh, I was going to say, that doesn't look part of it. Alrighty. Okay, so this was, as you might surmise, meant to prepare you for today. I say the limit is 1.001. Prove I'm wrong. Well, this is kind of getting into my aim. I don't know if I made my aim here, but what if you choose something close to 3, so close to 3 that 1.001 isn't even in there? Then it would be illogical to claim the limit is 1.001 when it's outside of the window you've made, yeah? So let's just choose something arbitrarily close so I know that wouldn't be in there. I'm going to go 3.0001 on one side and 2.9999 on the other side. When I do that, I don't have my calculator on here. I guess I could probably do this. Maybe I should have done this by something that's divisible by that, so I forget. So, -1 divided by 3 times 2.9999 plus 2. This is 1.00033, and this I imagine is something like something bigger. 1 divided by 3 times 3.0001 plus 2. I get 0.9999996. So in terms of, I don't know if it's a proof, but I could say that 1.001 is outside of this small window I've set. So it would be illogical to say it's approaching 1.001 from both sides if that's not in the region I made. That's kind of what I was shooting for. I don't know if that's what you did or if you didn't even know what to do. It was meant to lay the groundwork for today. Okay, you down? 25. Is 25 still a question?
Yes.
All right, 25. Did you use quadratic regression? Why not? I gave you a hint, for Pete's sake. What do I got to do for you people? Let's review regression because that's a handy skill to have. Shooby-doo. Dooby-dooby-doo-doo. I wish I would have reviewed this before class. I don't remember how to do this. It'll go fine. Let's do a document, shall we? This is good. Maybe I'll lean on you stat people to walk me through this. Look it up. That's ridiculous. That's not my style. My style is just play around until you succeed. So let's add a page. Let's add lists and spreadsheets, shall we? Let's call this X. Oh, shucks. Can I call this X? Okay. What are the X's for the points?
-1.
-1. What else?
1.
1.
3.
3. Check. Let's call this list y. What are the y values?
-1.
-1.
0.
0. 0. 6. Okay. Do you have those in your list? All right. Now you're going to have a calculator lay the equation through those. So just go off to the side a little into an empty cell. You with me? And go to Menu, Statistics, Stat Calculations. And is this what I want? No, I want, how can I do something besides regression? Linear regression. They're giving me linear regression. I don't want linear regression. How can I do something else? Actions? Oh, you're the teacher. Stat calc? Oh, I just went over here. There you go. Okay, quadratic regression. Boom. See that? Okay, X list is X. Y list is Y. Save regression equation to F1. That's if you wanted to graph it. That's fine. Category list. What's category list? What does that mean? Do I need to fill that in? I don't even know what that means.
I'm sure you can leave it blank.
Okay, I will. Okay, include categories. Don't know what that means either. Let's go with OK. Boom. There is your equation. AX squared plus BX plus C is 0.625 or 5/8 X squared plus 0.5X minus 1.125. Regression is a very handy feature when you go to use modeling. Through quadratic regression, the equation is, forgot again, negative 0.625. Was it negative? So long.
It was positive.
It's positive. Was the 5 mean? Also positive is the last one, isn't it? 0.5x minus 1.125. Okay, cool. That is 25. Any other questions? Wow, we finished so early. Yay. All right. Do you know why we get to do so much more in this class than the other classes? You guys are just geniuses. All right.
I should have worn false.
Scooby-Doo. Hi.
I was at yesterday. So I said 100. I got set 101 in the notes.
Yeah.
I want to get a T6 17 for school.
There's 101. Let's see if we yes, thank you.
Oh, Mr. Ricky?
Yes.
I don't think we turned up set 1.
We did?
Yeah, we did. You said you were gonna go over number 15.
Oh, did I? My bad.
Wait, did we turn that in or not?
Some people did, some people didn't. 115? Oh, that's the river one, right?
Yeah.
Okay. Yeah. Okay, so the idea is you're trying to estimate the volume of this river. If this were truthfully used, you would probably try and actually measure volumetric flow and how much water flows through this section rather than how much water is in and at what rate, but that's okay. They say at 10, or at 0, 10, 20, 30, 40, and 50, they take some distances across, yes? All right, so the idea is you're trying to estimate the volume in this if you assume semicircular cross sections. Let's start with the big idea. This is still, it's not a revolution volume so much as a cross-sectional volume. You cool?
Yeah.
The area of the base is pi r squared over 2 And the height is more like a delta x kind of thing. Now, we talked about how when you do semicircles, if you make it the diameter, is it pi over 8, the diameter squared, times h? Here's where then the calculus picks up, or the table picks up. Pi over 8, each time you're saying, what's the diameter squared? And you have to choose, do I use left or right? So the first I use is d at, I think I use left, yeah? Can I use left? So d at 0, but it's squared. Plus d at 10 and squared. Now all that's true. The heights for all of these are the same. What's the height for each of these? 10. So you might as well throw that out front. So your setup should be something like 10 pi over 8, diameter squared, diameter squared, diameter squared, diameter squared, starting at the left. Okay? Let's see, who's taking the test? Are you ready? Okay, I will start you with your ready. Here comes that. Yeah. Okay. Okay. You ready to go? I'll probably end up having you in the hall once fellowship. You want to start doing music. We'll go to the test tomorrow. Oh, that's on. That's not great. I'll think of something. We'll do our best. Have a lovely day.
It's basically a line.
All right.
I had another 2 pieces.